NoSQL Cloud database services are popular for their simple key value operations, high availability, high scalability, and predictable performance. So, actually, yes. DynamoDB, let's link to them. So, okay, so these characteristics are generally considered to be at odds with support for transactions. Okay, so this is actually a common theme. How do you add transactions to some of these systems that maybe didn't originally support transactions? So an example of a transaction would be that I want this, I want to perform some updates to the database, and all of them succeed or all of them fail. And I will wrap that in a transaction and give that command or set of commands to a database, and then it makes sure that that is true or not. And then they're also talking about two properties. So there's atomic and serializable. So let's see if I've actually talked about this previously. I think on the ramp tau paper, they talk about serializable. It's been a while since I've read this paper. I can't find a reference to it actually in my summary. So that means it's either not discussed in the paper or I did a poor job of summarizing the paper. But I think it's also in Foundation DB. Let's see. Serializable. Yes, okay. Amazing. So serializable. I'm trying to remember what I've referenced in the past as a good definition of serializable, but yeah, it's an important property of database. I think it's been in he writes about AFER serializable consistency models. So yes, this is, I believe, what and I think I think maybe I should figure out a way, because I'm talking about things on the stream that are I want to share, but not everybody doesn't have access to them. Not everybody has access to them. So let's see, serializable discussion. I'll post in the chat. Maybe that will be helpful. And then consistency models. So anyways, they want to add transactions to a NoSQL database that didn't have them before. And they're going to use a timestamp ordering protocol. And they want it to be low latency. So they don't want so they want to add transactions, but they don't want the addition of transactions to impact operations that don't involve transactions, which makes sense. And they also run this in production. Cool. I think there's also a reference to Peter Bayless's blog. Okay. Great. This is actually, I think this is the reference that I would normally refer to. So, serializability is a guarantee about transactions or groups of one or more operations over one or more objects. So, okay, so it guarantees that the execution of a set of transactions over multiple items is equivalent to some serial's execution. So that means that there is a way that transactions can be ordered. Yeah, they can be ordered, essentially, which is an important property. It's been a while since I've read this. So anyways, oh, forgot to start the timer. Okay, so they want to add adding serializability to DynamoDB. Transactions to DynamoDB that are serializable and atomic. Shouldn't impact non-transactions. Okay, so they talk about why are transactions important. Application developers rely on transactions to express certain ideas, and if you don't have transactions, then it can be difficult to reason about. And I think this is this is talked about in the paper that I wrote about related to tau. They talk about ramp tau, rather. Tau is a way of storing Facebook's graph connections, or Meta's graph connections, and they would have problems where there would be, you can imagine, okay, so I think in this example, you'd have a failure, right? So there's a graph that represents relationships between different entities. So for example, a user has some relation to some music, and they have another relation to a different set of music, and if you are performing rights and only one of the rights succeeds, then that will be confusing, because there will be, like, say you're trying to traverse the graph and there are broken edges in the graph, then you can't actually perform a graph search effectively. Is one, maybe one type of problem if you didn't have transactions, right? And you want to have rights where either all the rights succeed or none of the rights succeed. So developers rely on transactions. And if they don't have transactions, then it can be a bit difficult to reason about the system's behavior. So, okay, great. Simplify the development process. Yep. So, okay, great. This is exactly what is talked about in the RampTap paper. So, okay. Okay, yes. So they're talking about, there was this trade-off that happened where there's a trade-off where, okay, you're giving up some features for example, transactions in order to get high scalability. So if you want to perform a lot of writes and you actually don't really care about whether any of them are related and whether multiple writes that are related succeed or all succeed or all fail, then it's actually okay to make the trade-off of saying, that we don't need transactions. We just want to perform a bunch of writes. We want to put a bunch of writes in the database, or a bunch of data in the database. So that is a thing that has happened traditionally with NoSQL databases. So there's a system that is running at scale. And they also talk about Dynamo, but not DynamoDB. I'm trying to remember what the distinction is. I vaguely remember that Dynamo was the original system, and DynamoDB, let's see. Let's just Google it. And then Dynamo. Can you even get results for Dynamo? I vaguely remember that Dynamo was the original system. And then, and then DynamoDB was an evolution of that system. And I think that they make the distinction because they have different internals. And DynamoDB maybe is more advanced. Maybe that's why they're making that claim. Okay, so they decided to build transactions differently from other systems and cloud services. So what systems and cloud services do they build transactions differently from? Okay. Okay. So, difference between Dynamo transactions and other transaction systems. Everything is submitted as bundle. They also have a transaction coordinator. Okay, so they have two-phase coordination. And non-transactions don't use the coordinator. That makes sense. That could preserve the the idea that welcome new people to the stream. That can preserve the idea that, or the invariant rather, that you want to add transactions but not impact the performance of non-transaction calls. We're also reading, yes, I should have posted this in the chat. We are reading distributed transactions at scale in DynamoDB. This is in the chat. Cool. Okay, So okay, so okay, curious how they accomplish this. Transactions update items in place. Okay. So they're talking about this idea of multi-version concurrency control. So what will happen is, so multi-version concurrency control. So they talk about, let's just make sure to note that, about multi-version concurrency control. So actually a good example of a system that uses multi-version concurrency control is FoundationDB, which I've previously written about. So FoundationDB, refreshing my memory, they have do they actually, let's look at it. Yes, FoundationDB also has this idea of a coordinator. So I'm trying to remember how the transactions work in FoundationDB. Does this actually use multi-version concurrency control? Am I remembering a different system? Is it Tau? I definitely have written about multi-version concurrency control. Which paper is it in? It's definitely a databases paper. Okay. Okay, so it's Druid. Druid is, well, I mean, maybe it's been a while since I've read the Foundation paper, but yes. So, they also have coordinator nodes. So basically what happens is in multi-version concurrency control, you say that you write data, and then depending on whether, for example, the transaction succeeds, say you're writing 3 items and only 2 of the writes succeed. And oftentimes you use some version or timestamp to represent the, the version, you some numeric number or a timestamp to represent the version, and you'd say, well, either the, what is the item at this point in time, and so you can say, okay, we have gotten, I want to know this, on Monday, what did the database look like? And you can say, okay, well, for all items, or for items that are part of the query or would be returned as part of the query, look to see if there are multiple versions, and then only return results that are based on the version of the item that is from, maybe there was the last write to the item before Monday was on Sunday, so return the version that is from Sunday. And so this allows you to actually keep track of changes to something that's stored in the database over time, and can be very helpful for performance. It can be helpful for performance. For example, say that you have multiple versions. If there are updates to different items, you can say, well, we made updates to items 0 and 1, but the update to the second item didn't complete, so actually the new version never comes online. Or the new version, if it does, if you're waiting for some background process to, for example, replicate that new version to more nodes in your distributed system, you could say, well, that version doesn't come online until it's been replicated to some number of nodes. So it allows you to basically to make decisions about what the current state of your system is, and you can still allow reads that would be on some potentially stale state. So that's why multi-version concurrency control is cool. So, yes. But DynamoDB doesn't support multi-version concurrency control, apparently. MVCC. I'm not sure which is more difficult to pronounce, MVCC or multi-version concurrency control. And that's because the store servers would have to have had many changes to them. And also there'd be more storage. So the implication of single version store. Okay. Oh, I kind of went on a tangent and didn't actually. Maybe I should increase this for beyond 15 minutes, but the Pomodoro just went off. So what else? Transactions do not acquire locks. Louise has decided to read the paper with us. So they don't have any locking. There's some cons to locking. Do not acquire locks. There are cons to locking. So they're saying it requires a recovery mechanism to release the locks when an application fails. So you can imagine that, say there is an object A that you want to update as part of a transaction, and you have a lock, and then for some reason, while the transaction's happening, the component that is actually performing the transaction or coordinating the transaction, actually in this case it would probably be the coordinator, fails, crashes. So then you maybe have lost state about what transactions were in progress, or maybe the coordinator hasn't lost state, but it comes back online, and it takes a while for it to come back online to recover whatever it was doing before it crashed. And in the meantime, you have this lock on an object. So that's not great. So they decide not to use locks for that and other reasons. Optimistic concurrency control. So optimistic concurrency control is basically you perform writes, and then if it turns out that those writes conflict with other writes that you're doing or other operations that you're doing, then fail the writes. So basically you only suffer some performance hit, or you mostly suffer the performance hit if it turns out that you are performing many conflicting operations. So they use optimistic concurrency control. And then they use timestamps. Okay, so exploit the semantics of a key value store. So main contribution is making timestamp ordering reflect key value store. I actually think it would be very interesting for me to re-review what happens in the Foundation DB paper, whichever, wow, almost 2 years ago, over 2 years ago. So that would be really interesting. So it seems like yeah, it'd be interesting to see if is DynamoDB higher performance or supports more writes and or more of a workload than DynamoDB does. I'm not sure. Okay. Okay, so now it's all the introduction. And you can, this is basically the contributions right here. So we'll come back to this later. DynamoDB API, key value store, write operations, transactional operations. Oh, nice. They have some code. Very cool, very cool. I like the code. Transaction execution, transaction routing, timestamp ordering, right, transaction protocol. Yeah, so oftentimes papers that are in this vein will have some description of the protocol that they use. And that can be very helpful because you can say, look, there's this protocol that is used by the Foundation DB paper, and it is the same as maybe the DynamoDB paper, but oftentimes they're standardized protocols. Maybe with some alterations depending on the database. So for example, I know there's a MongoDB, or where is it in here? I definitely have the paper in my library. MongoDB, like they have some algorithm that is, somewhat standard, but they've made some alterations to it to make it work with MongoDB. It's been a long time since I read that paper, so don't hold me to that description of what they do. Where was I? Okay. Read transaction protocol, recovery, and fault tolerance. Adapting, timestamp ordering. And I have some experiments. Comparison of latencies. There was some controversy on the internet about the fact that they don't show the y-axis. I know somebody was saying that they were dissatisfied with the y-axis. I think it was in this paper. So, don't have any opinion about that yet. And then they have the related work and conclusion. Okay, so now let's get to the conclusion. Yep, they wanted to add transactions to DynamoDB without sacrificing predominantly all of its qualities. Okay, that's cool. Working backwards. I think that is even a working backwards. Is that even the Amazon saying? Yeah, that's like a insight stories and secrets from inside Amazon working backwards. So nice tip of the hat to the fact this is written by authors from Amazon. That's funny. Intentional or unintentional, not sure. But I think that's also very cool that they had their design based on, or they were able to base their design on real customer workloads and figure out that actually customers don't need these long-running transactions, because maybe that would have added some additional complexity. And these optimistic concurrency control. Okay. So yes, I'm wondering if there are other examples. There must be other examples of transactions in NoSQL databases. There must be. So maybe it is. Well, not Noria. FoundationDB is a key value store. So I'm curious. Yeah. So other NoSQL systems, I wrote this in the FoundationDB paper review. Other NoSQL systems didn't have transactions until recently. Cassandra, MongoDB, CouchDB. Also, FoundationDB is used at scale. So and a Snowflake uses FoundationDB or used FoundationDB. So I'm curious if there are any numbers about FoundationDB versus DynamoDB at scale. So that'd be very interesting to see. Cool. So let's look at some of the references. Relatively few references, actually. Any that they have some references to they have a reference to Spanner. Haven't read that paper, but I definitely want to. It's a Google database. They have reference to Dynamo, and they have reference to DynamoDB. CockroachDB. Yeah. Okay. Interesting. Okay. So, sorry, I missed some. I should probably read the original or reread the original Amazon DynamoDB paper. So maybe I'll write a series of posts about DynamoDB because, DynamoDB is there's a lot of papers about it. So, and it would be interesting to make the comparison with other systems. So okay, so let's go. So now let's look at the 5 C's. So yep, we did this. We did this, we read this, and then answering the 5 C's. So what did that? So basically, they added, in short, they added transactions to DynamoDB, distributed at scale NoSQL database from Amazon. And what are some of the other claims about it? And also no/low impact to non-transaction operations, which is important. And then they run it to the scale. Okay. So how are we doing on time? So we've been doing this is about 49 minutes to get through all of that with some detours. So let's take a little 5-minute break, and then we will read the rest of the paper. All right, we're back. So we're going to read about the DynamoDB application programming interface. Actually, it's relatively simple. There are puts, which is, and I know, these are just relatively simple API operations for a key value store. So you have puts, where you insert a new item or replace an item with an old item. Let's just say standard key value store operations. You can do updates, and you can do deletes, and you can do gets. So that's pretty standard for a key value store. So I guess technically DynamoDB is more than a key value store. It is a NoSQL database, but it offers key value like operations. And there's just arbitrary growth in storage. That's cool. A DynamoDB table. So yes, there are tables, and then there are items, and each item is a collection of attributes. Each item is uniquely identified by a primary key. Okay, it actually does say that DynamoDB is a key value store. So I'm not misrepresenting its capabilities. The last three operations are called writes. A condition that must be satisfied to be successful. Okay, so then on top of this, they also have transactional operations on top of this. I think it's really cool that they have code that really helps to visualize what it's doing. So you have get operations, get items, and write items. Okay, they're executed in serializable order. Okay, so this is actually okay. So importantly, reads fail if a write is modifying them. Any items of the items being modified. Being read, I mean. Okay. Okay, so how does the transact write items? Reads fail. Okay, then how does transact write items work? It's idempotent. So that means that if you have the same operation, the same write is issued multiple times, the outcome will be the same, essentially. And it uses the client request token. Ops. That's interesting. There are preconditions. Okay, they have some examples of using this in a store. Okay. Ha. Okay. Oh, and you also have check item. Check item, which verifies the value of an item matches the condition. So, okay, so they have a successful order in the store requires a customer account to be verified. Is that potentially the check item? The product to be available and marked, so that's the check item and marked as sold. That's probably a right. And the order itself to be created is also probably a right. Yes, check item, check that there's customer ID that is verified. You want to update the item, you want to create the order, and then you want to have this all in a transaction. Let's see. Luis is having a really good time with the squeaky toy. Okay. Oh, put item. Put item. Update item. I forgot about updates. Okay. But anyways, that makes sense. It's basically wrapping all of these things into a transact. So a transact, right, item is actually a read write. Performs which is, naming is hard. It performs a set of writes. Yeah, I mean, this is a read-write transaction, but yeah, naming is hard because it's checking, right? It's checking the TWE, the transaction write item request has a check item, it has a put item, and it has an update item. So, but anyways. Okay, so transaction routing, let's also start the timer. So transaction routing. So we're gonna learn about the architecture now, I believe. And so there's storage nodes, which I imagine handle actually storing and persisting the data. Okay, it's a pretty high level view of how DynamoDB works. Okay, so then this is the you got request routers, you have the auth system, you have the metadata system, and then in the transactions, you have this transaction coordinator. Runs a distributed protocol. Which one? Which distributed protocol does it run? I'm not sure if it's not mentioned because they don't want to say, or because it's talked about later in the paper. Oh, okay, cool. It's talked about. It's in here, so that's good. Okay. Cool. So now they're going to talk about how do they make sure that all these transactions can be ordered, and the way they do it is by each transaction gets a timestamp. And that allows multiple coordinators to be running at the same time. Okay, cool. Cool. They talk about clock synchronization. Which is also something that I talked about in a previous paper review about it's in here someplace. Sundial. And they talk about AWS's approach. And they say that accurate clocks are helpful for transaction success rate. I assume one of the ways in which a more accurate clock would help with success rate is that imagine if the clock is inaccurate, and so imagine if there are two transactions that conflict with one another, transaction A and transaction B. If transaction A in reality comes before transaction B and is capable of completing within before transaction B, then both of them can succeed. Because transaction A starts, it has the accurate time, and then it completes, and then transaction B is able to start and run to completion. But then you can imagine if transaction A is a coordinator, it's on a coordinator where that coordinator actually its time is it thinks that it's ahead in time. So that means that you have transaction. Will I be able to? I don't think I can actually do this in the air. But you can imagine that if transaction A incorrectly is assigned a later timestamp, then transaction A would start after transaction B had started, according to the inaccurate timestamps. So that means transaction B can't actually finish. So if you have more accurate clocks, then you don't incorrectly think that transactions conflict with one another. That would be my guess. So, yes, I'm curious if they do an analysis on that. So to do Okay, so then two-phase. Okay, so now we get to learn about the two-phase protocol. This is exciting. I'm excited to learn about how this works. Okay, so I'm going to read this and try to explain it. Okay, so for okay, this is cool. Okay. Okay, so there's basically a prepare. So you have app. So the first step is prepare. There's this two-phase protocol. What is the read protocol? I think that the write is probably more complex based on the length of the paper, just in each section. So you have two phases. Two phases. Prepare phase 1. Prepare. Then storage nodes accept/reject. And then based on whether the transaction coordinator gets all accepts, then it will tell the, this is pretty cool, execute completed, or execute if storage node storage node okay. So I'm already thinking about a few questions. So my understanding is what happens is there is this transaction coordinator, and what it first does is it says, okay, there are some keys that I'm going to change. So I'm going to find all of the storage nodes that those keys are on. And then I will talk to the storage nodes and I'll say, hello, I would like to write to those keys. And then the storage node will say, well, let me check my internal representation of whether it's okay to write to those keys. And then there's something that the storage, some information that storage node has. And if the storage node says, yes, actually, I just checked, and you went to write to key A and nobody else is trying to change key A or read key A, then go forward. And then I assume the storage node will write that metadata. You know, they're going to write that to their internal representation of whatever's happening with key A, and then they return to the transaction coordinator. But I wonder what happens if the transaction coordinator, for example, crashes during this process, or if there are other networking problems. I'm curious to what degree they talk about that in this paper. Yeah, so the storage node will say, hello, I am ready to accept. I really like that they have this pseudocode. It's very cool, I like that. Figure 2. So just turn by storage node, check some variants. So this is basically describing, I think, what I said. And interestingly, okay, so the storage node decides whether to accept if all preconditions on the item are met, if there aren't any technical reasons to stop writes to the item, if the transaction's timestamp is greater than the item's timestamp. So for example, if the transaction, it's kind of like a gate. So if the transaction started before the item's timestamp, that means the transaction is trying to operate on old versions of data. And so it needs to start again. And probably the way that happens is that the transaction coordinator is notified, there's a reject, then the storage node rejects, then the transaction coordinator says, oh, I have a timestamp. The reason I was rejected is because I have a timestamp that is older than, it's older than the timestamp of the item's most recent timestamp. So I need to go get I need to start over. So that is interesting idea. Also, it's fairly simple. So I like the simplicity. So if transactions accepted by all the participating storage nodes, yep. Items for which a precondition was checked, but that are not being written also have their timestamps updated. Okay. Commit cancel phase. So then that is listing 4. Transaction coordinator, okay, then basically that bubbles back up to the other services. Okay, cool. So that's interesting. One of the things that is that seems to be coming up is cost. So if you were to come up with a system where on deletes you maintain a tombstone, aka a record that corresponds to that deleted item, then there would be costs associated with that. It does seem like the cost would be fairly minimal, but maybe at scale that cost adds up. And I could also see that if you have many items that you are deleting, that would be true over time. Because then how would you get rid of the deletion records? It'd be hard to keep track of. So they don't have tombstones. And where are we? This is in the note. To do. Note that they don't have tombstones. Tombstones would be, for example, a record that says, this thing was deleted at this time. When an item is deleted, if the deleting transaction's timestamp is greater than the current max delete timestamp, then the max delete timestamp is set to the transaction's timestamp. Okay. I think I don't need to highlight that. So then, okay, so then there's basically this always moving forward max delete timestamp. So when a storage node receives a prepare message for a write to a non-existent item, it compares the new transaction's timestamp against the maximum delete timestamp to decide whether to accept or reject the transaction. Storing the max delete timestamp at a partition level provides a correct and efficient solution. In the current approach, transactions may be canceled in instances where they would not have been canceled if tombstones were maintained for deleted items. Oh, this is very helpful. I like this. Okay. Okay, so basically they're saying there are some cons. They note there are cons to this approach. So when a storage node receives a prepare message for a write to a non-existent item, it compares the new transaction's timestamp against the maximum delete timestamp to decide whether to accept or reject the transaction. Is that in here? I think that's, yeah, that must be in here. Okay, so if the item is not equal to none, and then we have some conditions, and the system restrictions are, we have those, then we check to see if the item timestamp is less than the input timestamp. Okay. And that basically up to here would be a valid transaction. So if item timestamp is less than the input timestamp, right? So that means that the new input is further ahead in time, and there aren't any other transactions, and that means you're good to go ahead. Now, if the item does not exist, that means that it either doesn't exist or it was deleted. So we do the same thing, and instead of, so now we look at the partition max delete timestamp. So if the max delete timestamp is less than the input timestamp, then that means we are recreating the key. We would potentially recreate the key, right? So this basically allows you to recreate a key that's already been deleted. Unless, so basically what this means is that if you go forward, say there's a delete of an item that's all the way over here, that's in the future, and then you try to change the a deleted item, then you won't be able to, because the delete changes the max delete timestamp to be the later transaction. But is that even allowed by the other parts of the algorithm? I probably need to draw this out on a whiteboard to really understand whether I'm getting this. But I think this is honestly a bit of a minor detail. So I'll come back. Come back to it. Okay. Read transactions are also performed using a two-phase protocol, although in a different manner from write transactions and from other systems. Okay. Okay. So basically check if anything you're reading if all good, return a monotonically increasing ID of that corresponds to the last write. So that means monotonically increasing is like 0, 1, 2, 3, 4, 5, blah, blah, blah. It can only go up. So in the second phase, the items are read again. If there have been no changes to the items between the two phases, namely the LSNs have not changed, then the read transaction returns successfully with all the items being fetched. Okay? In the case where an item has been updated between the two rounds of the protocol, the read transaction is rejected. Read again. That's interesting. So they're basically performing 2 reads for every read. Or maybe the first read is not really a read, it's just a get of the log sequence number. I see. So basically just keep reading until the LSNs are the same, sounds like. Which makes sense. Okay. So DynamoDB already handles storage failures. I should probably write about the DynamoDB paper. I think that would be good. Context. The metadata about transactions that have been accepted by the previous primary node. Cool. TCs are agnostic to storage node failures. Yep, transaction coordinator failures are of greater concern. This is one of the things I actually had a question about earlier. Yep. They have a ledger. They have a distributed log. Very cool. Okay. A recovery manager. Okay. TCs have a. Oh, it's maybe not distributed. It's just a log. Have a log of, but where? They have a persistent log of Okay. It's okay for multiple coordinators to be finishing the same transaction at the same time, since duplicate attempts to write an item are ignored by a storage node. Okay, cool. That makes sense. Has like scans for stalled transactions, must be some asynchronous process, or so the thing is, when you have multiple coordinators finishing the same transaction at the same time, but then duplicate. This is probably because of that's interesting. It's probably because of the item potency. Write to the log. So they're recovery managers. I like that this is all on DynamoDB. It's DynamoDB all the way down. Storage nodes also invoke recovery when local items have stalled transactions. Okay. Okay, so this is one of the things that they claim is novel. So I want to pay some attention to this. And then we're almost done. We're almost done because we're almost done because there's the experiment/evaluation at the end, which generally goes pretty quickly. So okay. Okay, so they're basically saying reads to individual items can always be implicitly. This get operation is assigned a read timestamp that is later than the write timestamp on the stored item and before the commit timestamp of the prepared transaction. Okay. Interesting. Writes to individual items can be performed immediately and serialized. Okay, I think that's, I'm going to read the section and then I'll say why I think that makes sense to me. Okay, yep. So if you put the primary node assigns the write timestamp that is earlier than the timestamps of any transactions in the prepared state. So note that a prepared transaction has not yet performed its intended write to the item. So that means that it's basically going to be whatever you are putting is going to probably be overwritten anyways. For the most part. I'm curious if they have any stats about that though. There's one. I see. Yep. So I see. So basically they have some like basically if a write jumps ahead of a transaction that's happening, it's probably going to be overwritten anyways, but can't jump ahead condition that comes later. Although, yeah, and again, I'm curious, how often does this happen? Okay, so yeah, basically you can move writes later. Basically queuing. But that seems kind of like you can just arbitrarily reorder if you have a mix of transactions and non-transactions and operations that are not writes that are not part of transactions. It kind of seems like you're just arbitrarily reordering them. But I guess that's fine. That's fine. Yeah, you're basically saying, oh, it's just you're overriding stuff. It's key value store. There's no point in time operations. So the takeaway here, I think, is that the key value semantics really simplify ordering of transactions. No point in time queries. That's my takeaway. So this is about, yeah. I see. So they're saying, well, but this seems like more of a potential thing than what's actually happening. This seems more potential improvement for the future? Question mark? But I'm a bit confused. Why are they talking about this idea of single round? Because it doesn't sound like that's what the paper currently is about. It's just, it seems like a future optimization. Maybe they just include this because they are aware that people are going to be skeptical of the fact that you have to have 2 rounds. Okay. Okay, I'm not super focused on this because it's not clear to me if it's actually implemented. So it's more of a theoretical thing that you could do. Anyways, experiments. We're on the home stretch here. So okay. Okay. It looks good to do figure 3. Basically, no matter the scale for reads, latency is about the same. Is approximately the same. Okay, that's what I take away from that. Okay, there's some thing that is at scale, but it's not. It's mostly because of Java, not because of the actual system. Okay. Okay. As number of operations in each transaction increases, so does latency. This is for So this is basically inside of a transaction, they are doing more operations. So more operations inside of a transaction. Yeah, this is to do figure 6. To do okay. Great. They're talking. It seems a bit like tail latency, because they're saying the number, basically because you have more operations inside of a transaction, there's a higher chance that one of them is going to take a long time for reasons. There's also some tail latency and writing to the ledger. Networking time. I'd be interested in the breakdown. Of each factor. My assumption is that it's for the most part tail latency. Okay. Okay, so then there are the 2 rounds of 2x latency comes from 2 rounds of communication. So I think that's probably why they're talking about having a single round. Because imagine that you would just get the same latency, the P50. Four x latency. Writing and checkpointing to the transaction ledger. Why does that take so long? I'm curious. Comparison of cancellation rate. So, okay, they just keep contention constant, and then okay, so keeping cancellation or keeping contention in the system constant. A few factors increase cancellation rate. Higher QPS. higher QPS. That makes sense. Oh, different workloads. Different workloads. So for example, they have A, B, and C. A, B, and C, which is different mixes. And then we have cancellation. Okay. Cancellation rate is a lot higher for, I see. So cancellation rate is a lot higher for, or is significantly higher for gets than it is for writes. Looks like. Transaction get items. Transact get items. Oh, actually it's saying that figure 10 highlights that read and write transactions will cancel at similar rates for workload B at all throughput levels. Okay. So there's some workload B is 50 or 50-50 writes and reads. Okay, so there's just basically some interaction between the workloads and the cancellation rates, and it seems to be reasonable. Yeah, that's my summary. Cool. So I think that that's really it for this paper. I'll be writing about it on my blog soon. Thanks for stopping by. Like and subscribe. Don't forget to like and subscribe. That's the YouTube thing. And until next time,